Picture a big room where every single point is a vector. Inside it, you already know two moves. You can add any two vectors, and you can stretch a vector by any number. Now suppose you get picky. You say, I only care about the vectors on this one line. Nothing else in the room interests me. And here is the whole question. Can you still do linear algebra inside it? Or do adding and scaling secretly throw you back out into the rest of the room? Sets where those two moves never push you out have a name. They are called subspaces, and learning to spot them is a core skill. Let's pin the words down. A vector space over the real numbers is a set of vectors carrying those two operations, addition and scalar multiplication, where the results always land back inside the set. The familiar examples are the real line, the plane of pairs x, y, and three-dimensional space of triples x, y, z. Their zero vector is simply the point with every coordinate 0. A subspace is a subset of a vector space that is all on its own, a vector space too, using the very same addition and scalar multiplication. Picture a line through the origin, sitting inside the whole plane. So how do we test a candidate? Let W be a subset of a vector space V. There is a clean three-part checklist, and W is a subspace exactly when all three hold. First, and easiest to check, the zero vector of the big space must lie inside W. If the origin isn't in your set, you can stop right there. Second, closure under addition. Take any two vectors already in W, add them, and the sum must land back in W. And third, closure under scalar multiplication. Take a vector in W, multiply by any real number C, and you must stay in W. Closed just means the operation never spills you over the edge. Three-dimensional space is where subspaces really come alive. So let's move there. Here are the three axes, meeting at the origin. The smallest possible subspace is just the origin by itself, the point 0. Add 0 to 0, you get 0. Scale 0, you get 0. It never leaves. We call it the trivial subspace. Step up one level, and you get any line through the origin. Every arrow along it, and every scaled version stays glued to the line. Step up again, and you get any plane through the origin, a flat sheet that contains the point 0. Any two arrows lying in it, added or scaled, never lift off the sheet. And the biggest subspace is the entire space itself. So the complete menu in 3 dimensions is short. The origin, any line through it, any plane through it, and all of space. Notice the theme. Every one passes through the origin. Let's watch closure happen. Take a plane through the origin, the flat floor. This green arrow lies inside it, and so does this gold one. Both honest members of our set. Now add them, tip to tail. Slide the gold arrow onto the end of the green one. And here is the whole point. The sum lands right here, and it is still flat on the plane. It never rose off the floor. Addition kept us inside. Scaling behaves the same. Stretch the green arrow or flip it to the other side. It only ever slides along the floor. Both moves stayed on the sheet. And that is exactly what makes a plane through the origin a genuine subspace. Now the contrast that trips everyone up. Start again with a plane through the origin, a real subspace. The green dot marks the origin, sitting right on the sheet. So far, so good. But now lift the whole plane up, away from the origin, like this. It is still a perfectly good plane, just shifted. And watch the green dot. The origin is now stranded below the sheet. 0 is not on this plane at all. And the very first rule of a subspace is that it must contain 0. So a shifted plane fails at the very first step. The same is true of any line or plane that misses the origin, no matter how flat and straight it looks. There is a beautiful way subspaces are born, from spanning. Take a single non-zero vector and ask for every scalar multiple of it at once. As the scalar sweeps through every value, big, small, negative, the tip traces out a full line through the origin. The span of one vector is a line, and a line through the origin is a subspace. Now bring in a second vector pointing a genuinely new direction, not a multiple of the first. Ask for every combination now. C times the first plus D times the second for all real C and D. The two lines flatten out and fill in a whole flat plane through the origin. So the span of two independent vectors is a plane, and it too is a subspace. This is the engine behind every subspace. Pick some vectors, take all their combinations, and a subspace appears. Time for the algebra. Work in the plane and look at three sets. Set A, the points where x plus y is 0. Set B, the points where x squared plus y squared is at most 1. And set C, where x plus y equals 1. Start with the contains 0. 0 plus 0 is 0. Yes. Now addition. Take 2 points on the line and add them. The x sum plus the y sum regroups into the two originals. 0 plus 0, 0. The sum is still on the line and scaling. C times x plus C times y is C times the quantity x plus y, which is C times 0, 0 again. All three conditions pass. So A is a subspace. It's the line through the origin with slope minus 1. Set B is the closed disk of radius 1. It does contain 0. But watch scaling break. The point 1, 0 sits inside. Double it to 2, 0. Now 2 squared is 4, bigger than 1. That point has escaped the disk. So B is not closed under scaling. It's bounded, and stretching leaves it. B is not a subspace. Set C is the fastest of all. Test 0 right away. 0 plus 0 is 0. But the set demands the answer be 1. 0 isn't in C. So we're done. It's a line parallel to A, pushed off the origin, not a subspace. Let's do the same check one dimension up. W is the set in space where x minus 2 y plus 3z equals 0. Contains 0? 0 minus 0 plus 0 is 0. Yes. Addition. Add two solutions and the expression splits into the two originals 0 plus 0. Scaling. Pull the c out front and it multiplies 0. All three pass. So W is a subspace and geometrically it is exactly a plane through the origin. Change one number. Set S wants that same expression to equal 5 instead of 0. Test the origin. It gives 0, not 5. So the origin is missing. S fails immediately. It's a perfectly good plane. Just W slid off the origin. And here is the clean rule to carry away. So the pattern is simple. Right side 0 gives a subspace through the origin. A non-zero constant gives an affine set that isn't 1. Your turn. Two sets in three-dimensional space. P, where z is 0, the flat floor. And Q, where x is at least 0, a solid half of space. Pause right now, run each through the three conditions and decide. I'll wait. Here's P worked through. The origin has z equal to 0. It's in. If 2 points both have 0 z, so does their sum. And scaling 0 keeps it 0. Every condition passes. So P is a subspace, the xy plane through the origin. If you said yes, that's exactly right. Now Q, the half space. It's sneaky, because it does contain the origin. But try a negative scalar. The point 1, 0 is in Q. Multiply by minus 1. You get minus 1, 0, 0, where x is negative. Not in Q. So Q fails scalar closure for negatives. Q is not a subspace. If that one caught you, remember, closure must hold for all real scalars, including the negatives. Trap 1. Assuming every linear equation gives a subspace. Only homogeneous ones, right side 0. Do. An equation like x plus y equals 1 is affine, shifted off the origin. Trap 2. Inequalities and squares. Sets like x squared plus y squared at most 1 contain 0. But they're bounded. A large enough scalar leaves the region, so scalar closure fails. Trap 3. Unions. The intersection of two subspaces is always a subspace. The union usually isn't. Take one vector from each, and their sum can land in neither. And trap 4. Skipping the zero check. Always test the origin first. If it's missing, you're finished, not a subspace, and you've saved yourself all the other work. Let's lock it in. A subspace W must clear 3 bars. It contains the zero vector, and it's closed under addition and under scaling. Geometrically, in 3 dimensions, that means the origin, lines through it, planes through it, and all of space. Everything anchored at 0. And the quickest tell. A homogeneous equation gives a subspace. A non-zero constant gives an affine set that isn't one. Run the checklist 0 first, and no imposter set will ever fool you again.